So in this segment, what we would like to present is an interesting solution or use case which we jointly developed for LINX with Edgecore and Broadcom. So this is a key work we have done over the last couple of years. So I would like to, this is structured in two parts. The first part, we would like to explain background of LINX and hear the customer's perspective, what they think about this, the whole white box and disaggregation and the whole process of moving networks from traditional model to the disaggregated model. And then the second part, we would like to highlight some of the key features and aspects, the details of the solution. So let's get started. So LINX, as most of you know, is the London Internet Exchange, and they are one of the largest IXPs or Internet exchanges in the world. They operate, they have 780 plus members. They operate in, 75 countries, and it's really one of the largest network within the IXP segment. And just to set the context, so LINX operates two big networks. One is what they call the LON one, it's the London one. And the second slightly smaller network is the LON 2, it's the London 2. And as part of this process migration, we help LINX move the London 2 network from the traditional boxes to white box using Edgecore. So some of the key facts which we want to highlight here are LINX is the first IXP to use network disaggregation. And again, we are happy to power this mission critical network using a combination of OCNOS software running on Edgecore devices and with the help of Broadcom silicon. So we just want to highlight that it's in production. It's running for over two months now, since the beginning of June. And LINX is one of the first IXP to adopt this new technology, EVPN VXLAN. This technology has been available previously on other devices, but at this scale and at this level of integration, they are the first IXP to use this. And then finally, yes, it's again a validation for our carrier gate performance. So with this, I would like to actually play this video from LINX. We would like to hear their perspective on what they think through this process. So it's a short video. After this, we would continue with the rest of the details.
LINX decided to do the disaggregation model really for two main factors. One, we know that the marketplace is changing. The prices of peering is coming down. And two, we needed to look at new infrastructure, a new way of scaling. We feel that by adopting the disaggregated model, we can drive better cost base into the peering infrastructure, which we can then pass on to our members as benefits in reducing port prices. For LINX members, adopting this new technology will bring many benefits. We'll talk a little bit more about the various technicalities of how EVPN multi-homing can benefit the membership. But essentially, we're going to be driving better cost models into the network infrastructure. We'll be able to then pass on reduced port fees, and we'll also be able to have stability and scalability that will benefit the members for many years to come.
So EVPN, Ethernet VPN, is a new method of actually controlling an Ethernet switch network. The old technology required the switches snooping on traffic, figuring out that if traffic was going from port 3, then the return traffic had to go back to port 3, or whatever the port was. And that is a bit ad hoc and can cause complications and challenges on the network. Whereas instead, with EVPN, everything is programmed and all the switches talk to each other, synchronize, so that it is a lot more predictable, a lot more stable, and it then allows extra features to be built on that information. So we chose to work with Edgecore Networks and IP Infusion for two reasons. Primarily for their experience. Edgecore are a long-established Ethernet switch manufacturer, and IP Infusion are, again, a long-established software stack provider. They had the technical expertise to take us through the project. But equally important, they shared our vision. They actually believed in what we were trying to do in the disaggregated solution, the potential for the market, and were willing to go through the journey with us and put the effort to get us to success.
Looking at the project, there have been a number of challenges that we've faced over the last 2 years. One of the key ones has been around getting our automation to work. So we'd already adopted a fully automated configuration platform for London 1, and one of our key drivers for the new network was to make sure that we deliver the same automation across that platform as well.
The biggest challenge was at the beginning. We knew what we wanted to do, but we didn't know exactly what was possible. So it was quite an extensive learning process together as we really got to find what the scope was. And then building on that, just going through testing, getting all the bugs, all the little niggles out, so that when we migrate to the network, we are confident we'll offer a good service day one.
So we learned during the migration phase that we had to switch from a development and proof of concept mindset into an operational mindset for the three companies. I think that was quite challenging because it was new for us, it was new for IP Infusion, it was new for Edgecore in how we adopt this new operation model. But we've got there. We feel that we have a workable model now. We feel that we're performing well, and we've got great support from IP Infusion, who are our lead point of contact for any operational issues. Currently on London 2, we're reaching, as we get into June, the end of the member migrations, where we've taken all of the members from the old Extreme Networks LAN and moved them onto the new IP Infusion Edgecore LAN. We have a second phase where we're going to be adding further technical capability to the LAN as we go through the year. But at the moment, we're excited to complete the migrations.
So that was a short perspective from our customer LINX. They were not able to be here present for this event, but they shared this video and let us present this solution. So let me continue with the details of the solution now. I'm pretty sure most of you are familiar what an IXP is, and so just to very quickly recap, an internet exchange is essentially a neutral network, a neutral place where different parties come together, like content providers, service providers, and anyone who wants to exchange routes, internet scale routes, in a scalable and cost-effective manner. So that's basically an IXP. So in essence, it's like a large switch and a neutral location. And the exchange operator, what they do is most of the exchange operators are more or less member-driven, non-profit, and they try to create this neutral location for members to peer together. And why do we need peering? Because in the old days, the transit routes were either direct or tri-party arrangements, and this couldn't scale as the internet traffic grew, and so IXPs solve this problem, and it's a cost-effective way to exchange routes. So if we look at the design of an IXP, there are two models. One is a layer 2 network, and the other is a layer 3 network. By default, today, layer 3 is not preferred. So layer 2 is the preferred mode of designing these type of networks. The reason is simplicity and also managing this the whole member connections, and so you get a lot of tweaks when you do a layer 2 network, and it's much simpler to manage and exchange the data. So if you look at some of the aspects when you design an IXP, so of course you have a huge amount of member traffic coming in. You need to moderate the traffic, take care of security, and then also handle this scale, the domain, the layer 2 issues like broadcast and VLANs were used before. So those are some of the aspects which needs to be addressed in a typical a layer 2 network. So looking at this solution for London 2, what we did here was we essentially, London 2 is spread across 10 data centers in the metro London area, and so we provided this the layer 2 fabric using Ethernet VPN. So it's a huge layer 2 fabric spread across 10 data centers, fully meshed any-to-any connectivity, and we have used it's basically essentially, as you will see, it's a extension of a leaf-spine data center fabric, and we have added some tweaks to have fast convergence and implemented special protocols for LINX to make this possible. And also, in terms of automation, this is it uses standard interfaces like SNMP and netconf, and on top of this, we have a full scripting engine to fully automate this management day-to-day operation.
So I'm just curious. I have a question about the convergence. Can you share what some of the things were that you did to improve the convergence over that stretched fabric?
Sure. Yeah, I'll go over that. Yes.
Okay. Great.
Yeah. Thank you. So this again is this is not the real topology. It's a 3-site representation of the actual network. So if you were to expand this to 10 sites, essentially this is the basic architecture. So as you can see here, you have these yellow edge sites. The edge sites are where the so-called members plug in their ports. So the members come in with their equipment. It could be a L3 router or other means of exchanging traffic, and they get these ports and plug into one of these data centers. So from there on, all the boxes here shown here are based on Edgecore devices running OCNOS, and they are powered by the Silicon Trident 2 Plus and Tomahawk. That's predominantly what we've used for this solution. And if you look at some of these interconnections, so the backbone is purely 100 gig. One of the reasons for moving to this model is they wanted to reduce the cost per port and cost per member when they migrated from 1 gig to 10 gig, and also for future expansion. So this is helping them achieve that cost model. And and each of these edge sites is in fact redundantly connected to the spine sites. So you have a lag connection between the yellow edge sites and the spine sites. And the back end is, as we said, is 100 gig. The interconnection is essentially using optics. They use DCI from a different vendor. It's a coherent optics interconnecting all these 10 sites, 10 plus sites. So that's the basic architecture. And if we look,
can you go back to that? I was just noticing at the top site, you have a leaf spine architecture, but you have the leaves connected together, which isn't typical what you would see in a CLOS architecture.
You mean the interconnection between the leaf sites?
Right.
Right. So I mean, it's essentially not a typical class. It doesn't mirror the interconnections. Doesn't mirror a perfect class like you would see in a data center. But in principle, the reason I think is to redistribute the spine traffic, and also to achieve the same level of redundancy when these sites are spread across. And also, I believe it's depending on their the layout of the fiber which they have in the metro region. So you're right, it is not a perfect class like you would see N-way class, and but the idea is to mirror that.
Are they doing MLAG across that piece? Or is it L3 routed? Like most times you see a design like that, it's because you're doing first hop redundancy in the leaf, the edge leaf.
Right.
And you're holding your layer 2 continuity between the two, and then you're running L3 up from there. That might be the cause. So quite commonly when you're scaling out it, you want to have L2 for redundancy down to the spines. So you just run MLAGs between the two.
Usually that's an edge leafs, but these are not. These are connected back.
Yeah, these are all BGP peering routers.
Yeah.
Typically exchange
BGP
tables. So
yeah.
my expectation is that you're plugging a router into this fabric because you want to peer with the route reflectors for LINX as well as all the other members and peers of the IX. So,
But you don't want to burn IP addresses on VLANs because they all have to be public addresses. You want them to be unnumbered, so you want them to be Ethernet at layer 2.
well, I think that's what they are. But I think that that's
It's BGP EVPN. It's VXLAN.
We did away with VLAN and moved to
First hop redundancy. You've got to have first hop redundancy.
that's
right. But
one
I mean,
reason.
my expectation is you would just establish multiple peerings into that. You would establish multiple peerings, have a couple routers, and then peer between them and
We're
establish.
assuming that the people at the IXP are that intelligent.
Well, I'm just saying, based on what I see IX people peer into IXs on, that's what I typically see is only my point.
Okay.
Sometimes, yes.
No, to summarize a valid point, so good question. So basically the redundancy is built from the edge. So you have this lag. Actually, we don't use MLAG because it's just too complicated.
Yeah.
But you have multi-homing or lag at the edge. And then the spines act as the distribution layer for this 100 gig traffic. And it doesn't mirror a perfect class. It's just a distributed class you can think of. So, okay. So
We can map it out tonight over beer.
Oh, yeah, absolutely. Folding whiteboard.
We're gonna redesign an IX.
Yeah.
So again, the underlay is based on standard OSPF, so that's the IGP we use here. And for the overlay, like we will go into the details, it's based on the MPBGP EVPN. So that's the control plane we use here. And of course, all the other tweaks related to IXPs regarding port control, storm control, and QoS at the edge. So you need to rate limit the member traffic when they come into the network. And those are some of the things we specifically fine-tuned for this solution.
So I'm curious why. Sorry, go ahead.
Oh, sorry. Is anyone else surprised that it's OSPF?
Well, that was mine.
A little bit. Yeah.
Everybody was.
No, I was going to say why not IS. My question was why OSPF versus IS for the. I'm assuming the IGP for the AS to carry loopbacks in transit. For the AS.
No, that's a good question. I'm not sure why they chose OSPF. It's probably because they already had OSPF before and they're more familiar with it, and instead of ISIS. So
yeah, and to be clear, I'm not against OSPF for IGP transit for that. I'm just curious why the choice was made between the two.
Okay.
It's more a case of why would you choose ISIS?
It's higher. It could be hierarchical. It scales more in
It's
IGP.
for scale, it's an IXP. It's only going to be a couple of thousand Ethernet ports.
Yeah, it just depends on your flooding domains and where what the flooding domains look like and what do the flooding domains heavily used, and if they are, do you may want that hierarchy, and where do you want flaps in the network? Where do you how do you want to contain those flaps in the network? So that's
We'll argue about that later.
sure.
It's a shame that Ivan Pepelniak is not here because we could have started a religious argument about
IGPs.
whether or not we need an IGP at all.
Yes.
Right.
Okay, that's.
Do you have any insight on why they decided to go for an IGP for the underlay and why not they did not go for eBGP all the way? Maybe you have some insights, but maybe you don't. I don't know. I'm just asking out of curiosity.
Yeah. Again, I think there were other considerations. So one is it's not just. I mean, it's easy to see of this as a pure data center, right? But essentially, you also need a solid an IGP, a routing domain. So one reason is we need the routes essentially to power the BGP for the EVPN, right? So that's the one reason I believe they use one of these IGP and they chose OSPF. So with eBGP, I mean. You still need that's mostly point-to-point connections. So these are slightly. It's not just point-to-point connections. It's more like a mesh as well, except it's distributed. So those are some of the reasons I can think of why they would choose.
And they're also running their own AS. They're running their own RIPE AS. I mean, they've got to still establish an IBGP AS inside this, and also to provide the framework. So I imagine they'd have to have an IGP.
Yes,
to form the AS.
So are they running a separate OSPF v3 instance for the IPv6 infrastructure?
No, not yet. At this point, at least for London 2, they've started with V2. and in future they might use migrate to V3 or V6.
So right now they're only supporting legacy IP at an IX?
No. I think it's they're transporting layer 2 over for the members to peer with each other.
Right.
Then the members can do whatever they want.
Okay, I see where we're going.
Yeah, this
This is just forming the underlay and the transport.
I see.
The hardware that's in place doesn't have IPv6 VTEP support.
Okay. So basically this is just underneath, and then they're okay.
This is the fabric, underlay fabric.
Sure, understood.
Yeah. To build that, I mean, you could have used eBGP, except it's very specific design based on a standard class, right? This is more generic. You get to, I mean, there are other aspects here. For example, with respect to fast link recovery, to your question, we have used BFT and also layer 3 BFT for faster link recovery and convergence. So some reasons as well. So let me move on to the, and then a few more details of the solution. We have enabled S-flow, and of course, like you saw, because of the lag and all the member ports, we have provided full load balancing across the whole fabric.
Sorry, just one quick one. What's the hashing algorithm? Is it like a specific one, a custom one that you developed?
No, it's not a
right.
custom. It's what we have enabled from the silicon. So it's RTAG 7 based. It's a combination of ports and the IPs. So, and some background, I think I'm running out of time. So some background on EVPN VXLAN, which we have done for this specifically. So as you all know, this is a standard protocol. The advantages of using EVPN specifically here is once you migrate from a VLAN broadcast domain, they wanted to control the amount of broadcast in the network. For example, ARP broadcast, you can do away with using EVPN's ARP proxy. So that's one advantage, and then better scaling, distribution of the host routes using the control plane, and all the standard features that come with EVPN. So those are the advantages, and also looking into the future, they wanted to enable more redundancy. Multi-homing is coming up next as the next phase, and and general scaling as well overall with what you get from VXLAN. With that, I want to leave away with this final thought, which is the London 2 is fully migrated across 10 data centers, and the peak traffic rate that you see is around 600 gigabits per second running on these. So it's a good solution for us and overall for the industry.